Hey, what's up guys? This is Dr. Vivek Palipuram and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineering and Computer Science. In this lecturette, we are going to discuss some additional random variables, some more families of discrete random variables. In my previous lecturette 9, I introduced you to three random variable families, and those were Bernoulli trials, geometric random variables, and binomial random variables. A Bernoulli trial is used to model those experiments which have exactly two outcomes. Either they are going to be successful or they are going to be failure. For example, if I were to toss a coin, I'll get either a heads or I'll get a tails. If I were to roll a die, I may get a 6 or I may not get a 6. So that's an example of a Bernoulli random variable where x is equal to 0 to denote typically failure and x is equal to 1 to denote success. Things get much more interesting when we perform multiple Bernoulli trials, and depending on what experiment we are doing, it gives rise to different kinds of families of discrete random variables. For example, let's say that I keep performing my experiments, my Bernoulli trials, until I get my very first success. The number of trials that have gone behind obtaining the very first success is represented using a geometric random variable. For example, I may keep tossing a coin until I get my very first heads. So the number of times that I have to toss the coin is represented using a geometric random variable. So I may want to use the probability mass function of a geometric random variable to solve all kinds of probability problems for that particular experiment. If I were to perform fixed, constant number of Bernoulli trials, and let's say that I'm interested in k number of successes, k is going to be a random variable. Specifically, it's going to be a binomial random variable. For example, if I were to repeatedly toss a coin 20 times, I might be interested in k number of heads. So I may be interested in answering questions like, hey, what's the probability that I get 15 heads? Or what is the probability that I get no heads at all? Or I may be interested in finding the probability that I get less than 5 heads. Such problems will be solved using binomial random variables PMF. All I need to do is just adapt the PMF of binomial random variable and solve different problems pertaining to that experiment. So these were the random variables that we had discussed in our previous lecture. Now, looking at this video, you may be wondering, what is random signals? Has Dr. Palipuram mispronounced, or did he misspell signals? Perhaps he wanted to use his notes from his random signals course. Well, actually, I did intend it to be random singles because I'm going to show you some scenes here and we are going to answer some probability questions. So here we have our beloved characters, Penny and Howard. And Howard is like, hey, will you have dinner with me? And Penny's all, not even if you ask me 1,000 times, Howard. Now, Howard, being an engineer, is all optimistic. And he's like, so there is a success probability. So the success probability per asking out is 1 over 1,000 or 0.001. Help Howard model this situation. How many times n should I ask for dinner until the very first success, given each time I succeed with probability 0.001? N is definitely going to be a random variable. Pause your video here and think about which discrete random variable family would you recommend Howard to model the situation. Once you're ready, you can unpause your video and I'm going to show you what Howard has found. Yep, n is indeed a geometric random variable because Howard is continuously asking Penny out until she finally goes out for dinner with him. So the number of trials here until the very first success is going to be a geometric random variable. Let's take a look into another scene. Now we have Howard and Bernadette, and Howard is all, Bernadette likes me, but she doesn't always want to go out for dinner. So far, the success probability has been 0.6 each time I ask, independent of any other asking out. Help Howard model this situation now. How many times K will she go out for dinner if I ask her 100 times if each of those 100 asking outs are independent of each other and they are exactly the same Bernoulli trials? You can pause your video here and think about which random variable you would like to use. Once you're ready, you can unpause your video and I can show you what Howard thinks. Oh yeah, K is going to be a binomial random variable. We are going to use a binomial random variable in that case because the number of trials, the number of asking outs is fixed to 100 and we are interested in K successes. So K is going to be a binomial random variable because that's what binomial random variables are used to model. So we can adapt, or rather Howard in this case can adapt the PMF of a binomial random variable and solve all kinds of probability questions with respect to that experiment. Let's solve some instructional problems now. So Dr. Larwood created 24 questions for his mechanics class. Each question is equally likely to be of 4 difficulty levels, E, M, D, or G. What you need to do is find the PMF of G and find the probability that none of the questions are of G difficulty level. You can pause your video here and try to solve this problem on your own. See if you can apply the PMF of a known random variable. See if a known random variable can be used to model the situation. Once you have given a sufficient attempt, you can unpause this video and I can show you the solution. Okay. So n in this case is 24. So Dr. Larwood hypothetically has set a question paper with 24 questions where each question is equally likely to be of easy, E level, or M level, or D level, or G level. Each of them are equally likely. Now we are specifically interested in G level questions. So probability of getting a G level question is 1 over 4. So that's if one question were to be considered as a Bernoulli trial, its probability for it to be of G level is 1 over 4. So probability that it is not going to be a G level is 3 over 4 naturally. And we are interested in deriving the PMF of G, the number of G level questions. That's what we are interested in, G level questions out of 24. Now, because each question is independent of the rest, and each question is an independent trial, or a Bernoulli trial to be more specific, because it's either going to be of a G level question or not. So here we are modeling, or we are going to use binomial random variable to model this situation because we perform 24 fixed trials. We have 24 fixed number of questions. G is binomial, and therefore I can adapt the general probability mass function formula for the binomial random variable, which goes something like this. It's going to give me probability that the number of G level questions is a specific value, small g, and that is obtained using the probability mass function of G, which is n choose k times p to the k times 1 minus p to the n minus k, where k is 0, 1, 2, and so on until n. That's what k takes on. But in our case, n is equal to 24 because we have 24 fixed questions. P is 1 over 4 because we are interested in modeling the probability of getting a G level question. And therefore, the PMF of G takes this form. 24 choose G. Well, this should be, this term right here, it should actually be G. This term is G because that's what we are using. That's the variable name that we are using to denote the number of G level questions. Okay, so the PMF of G is going to be 24 choose G, 1 over 4 to the G times 3 over 4, because 1 minus P simplifies to 3 over 4 to the N minus G, or 24 minus G, where G can be 0, 1, 2, and so on until 24. Either you can get no questions that are of level G, or you may get all of them that are of level G. So that's the probability mass function, the generalized probability equation to solve probability problems with respect to this particular problem. So that's part A. Once you have derived your PMF, everything else just becomes plugging and chugging of proper values. So the only challenge will be to plug in the proper values, and that's about it. In part B, we are interested in finding the probability that none of the questions are of G difficulty level. So we need to find the probability that G is equal to 0. None of them are G level difficulty questions. So all I need to do is just plug in the value of G as 0 in my PMF equation, and that will give me the probability of G as follows. So that's the probability of 0 G level questions. It's perfectly acceptable to leave your answer in this format. So that's the application of a binomial random variable. Moving on, I have another scene for you. Now we have two characters, Leonard and Penny, and Leonard is I want to ask her out for dinner. I think she likes me, so my rejection probability Q is probably low. But I'm not obnoxious, so I'll ask her until I get rejected K times, and after that I'm going to move on because I'm going to take a hint that this lady is not interested in going out with me that much. So how it is like, if I get shot down K times, I'm going to move on, and this K times can appear however. Essentially, how Leonard is interested in modeling L the number of times he asks Penny out until he gets K rejects, upon which time he decides to finally move on. So that's the problem. We want to help Leonard model the situation where his experiment is to ask Penny out for dates, where each asking out having a rejection probability Q. So observe L, the number of times he asks for dates until there are K rejects. What you need to find is what is the PMF of L. So the number of times Leonard is going to ask Penny out for dinner, L, is going to be a random variable. It can be either K, in which case he gets K rejects one after the other, or he may get his Kth reject on K plus 1th asking out, or at K plus 2th asking out, and so on and so forth. Essentially what we are interested in is finding the probability mass function of L where you get where Leonard gets his Kth rejection in this case. So focus on the PMF for this particular problem. As you work on the PMF, let me give you a hint here. This whole experiment of Leonard asking Penny out L times, and on the Lth time he getting his Kth reject, upon which time he finally moves on, can be divided into two sub-experiments. It's important for us to understand that Kth rejection is happening on Lth asking out, because we are interested in modeling L, the number of times Leonard asks Penny out until he finally gives up. And he finally gives up when he gets K rejections. So that would mean that in first L minus 1 asking outs, he may have gotten K minus 1 rejects placed anywhere. With each asking out having probability Q for rejection. So this can be considered as your sub-experiment number 1. He asks Penny out L minus 1 times, in which he gets K minus 1 rejects anywhere. So think about what random variable you can use in this case. That's sub-experiment number 1. Then sub-experiment number 2 would be to get final rejection here, his Kth rejection here. So this entire experiment can be broken into two series sub-experiments. Sub-experiment 1 first, where he asks L minus 1 times and he gets K minus 1 rejects anywhere, and he gets his Kth rejection on the Lth asking out. Now both of these sub-experiments 1 and 2 are independent of each other because each asking out is independent of each other. So probability of the entire experiment will give you probability of Kth rejection on Lth asking out. It can be given to you by evaluating the probability of sub-experiment 1 times the probability of sub-experiment 2, because experiment 1 and 2, they are independent of each other. What you can do is pause your video and find these individual probability terms, and when you multiply together, you would find that you would have derived the PMF of the previous problem, of the Leonard's modeling problem. You can pause your video here. Once you're ready, you can unpause and I can show you the solution. Okay, I hope you guys got the chance to solve this problem. As it turns out, sub-experiment 1 is actually a binomial random variable because we have L minus 1 fixed experiments and we are getting K minus 1 rejects anywhere. So I can use the binomial's PMF to find the probability of sub-experiment 1. So I have L minus 1 asking out, and I get K minus 1 rejects. Q is the probability of a rejection. I have K minus 1 rejects, so that will go to in the numerator, in the power term, times 1 minus Q to the L minus 1 minus K minus 1. So that's the probability of sub-experiment 1. Probability of sub-experiment 2 is just Q, because it is given to you that each asking out has the probability of Q to having a rejection there. So since sub-experiment 1 is just one single asking out, its probability is Q for a rejection. So times Q. So if I were to simplify this further, I get PMF of L that Leonard asks Penny out for L times, upon which time he gets his kth rejection, is given by L minus 1 choose K minus 1 times Q to the K, because when you multiply Q with Q to the K minus 1, you get Q to the K, times 1 minus Q. I can simplify the power term as L minus K. So that's the PMF. That's the PMF for this particular problem. And here, K is random, and it can be either, or rather L is random, my apologies. L is random here, where L can be either K or K plus 1 or K plus 2 and so forth until infinity. It's important for us to understand that the minimum value of L is K, because Leonard has to ask at least K times to get K rejections. Now, using this PMF, I can solve this probability problem here. So the PMF of L I found out as L minus 1 choose K minus 1, Q to the K times 1 minus Q to the L minus K, and Q is 0.25 here. That's the rejection probability. K is equal to 3. So when I plug in the values, I get L minus 1 choose 2 times 0.25 to squared times 1.75 to the L minus K. So I want to find the probability that Leonard gives up on his 7th asking out. So I need to find the probability that L is equal to 7, and that will be equal to 6 choose 2 0.25 squared 0.75 to the 5th. That's the probability for this answer. Once you find your PMF for a problem, it's just a matter of plugging and chugging the correct set of values, and that's about it. That's how PMFs make our engineering life much more easier. Once we know which family of discrete random variable to apply, the problem becomes extremely simple. In fact, Leonard tells us that L is a very special type of random variable, and that is called as the Pascal random variable. L is Pascal random variable, and Pascal random variables are used to model those situations where you perform variable number of independent trials until you get your kth success. So the number of trials that you perform until k successes is going to be random. Specifically, it's going to be a Pascal random variable. An example will be as follows. I have a coin and I keep tossing it until I get my 10 heads. I can get my 10 heads on the 10th flip. I can get my 10 heads after I flip 11 times. I can get 10 heads after I flip 12 times, and so forth. So we are interested in number of trials until k successes or k outcomes. For Thursday's class, this is what I would like for you guys to do. I would like for you guys to solve this problem and submit it along with other set of problems in the videos. The next random variable that I would like to discuss here is the discrete uniform random variable. Now, I'm not going to spend a lot of time on discrete uniform random variable because in probability theory phase 1, you have worked a lot with discrete uniform random variables. Specifically, discrete uniform random variables are used to model those engineering situations where you perform an experiment, you get multiple outcomes where each of these outcomes are equally likely. For example, if I were to roll a die, a fair die, my outcomes are 1, 2, 3, 4, 5, and 6. These outcomes are equally likely with each with probability 1 over 6. A discrete uniform random variable's probability mass function takes this form right here, where probability that x takes on a very specific value, small x, is 1 over L minus k plus 1, where L is the upper limit or uppermost value that you can observe from experiment corresponding to a uniform random variable, and k is the lower value. For example, when I roll a die, L is equal to 6 and k is equal to 1. So PMF of x in that case for rolling a die experiment is 1 over 6 minus 1 plus 1, which is 1 over 6 for x is equal to 1, 2, 3, 4, 5, and 6, and it is 0 otherwise. We are not going to spend any time solving probability problems for uniform random variable in this video, but I may solve these problems for you when we actually meet in the class for Thursday, because you have already been exposed to uniform random variables of discrete nature. I would like to definitely focus on Poisson random variables because Poisson random variables are quite useful in a lot of engineering cases. I can find use of Poisson variable in different engineering fields. For example, in my own field, computer engineering, I am usually interested in the number of packets that arrive at a router in a particular time period, given that the arrival rate is fixed constant. Similarly, a transportation engineer may be interested in the arrivals or in the certain number of arrivals of buses at a weighing station in a given time period. Civil engineers may be interested in the number of occurrences of rainfall events over a given month, given that the rainfall event has a fixed rate of arrival. In such cases, we use Poisson random variables to model the number of arrivals or the number of occurrences. Remember, Poisson random variable is a discrete uniform random variable. It has to count something. Specifically, it's going to count the number of arrivals or the number of occurrences, given that you have fixed rate of arrival or rate of occurrence information. So let's formally define what Poisson random variable is. The Poisson random variable x is modeled using its parameter alpha, and it has its probability mass function as PMF of x is equal to alpha to the x times e to the negative alpha or x factorial, where x can be 0, implying 0 arrivals, 1 implying 1 arrival, 2 implying 2 arrivals, and so on until infinity in a given time period. It is 0 otherwise. Now alpha parameter is a product of lambda and t, where lambda is the rate of arrival and t is the time interval over which you're counting or you're interested to count the number of arrivals. So alpha is equal to lambda times t. In fact, alpha is your average arrival or average number of arrivals over period t. Using this PMF, we answer different questions like, hey, what's the probability that in a time interval of 0.25 seconds, I have exactly 5 arrivals, and so on and so forth. Let's solve an instructional problem using Poisson random variables. So the number of packets arriving at a router in a particular time period is Poisson, and it gets packets at the rate of 2 packets per second. So that's your rate information, the lambda. What you need to do is find the probability that there are no packets in an interval of 0.25 seconds. What is the probability that there are no more than 2 packets in an interval of 2 seconds? So I'm going to solve these 2 parts here. Part C is for you to solve and submit it for Thursday's class. So lambda is given to us as 2, and for the first case, part A, I'm using the time interval 0.25 seconds. So alpha will be equal to lambda times t, which means that alpha is equal to 0.5. So let x be number of arrivals. X is Poisson because I have fixed rate information. The rate of arrival is fixed. So PMF of x gives you the probability that the number of arrival is a specific value, small x, and that is given by alpha to the x, so 0.5 to the x times e to the negative alpha over x factorial, where x can be 0, 1, 2, and so on. I need to find the probability that there are no packets. The probability of no packets would imply that x is equal to 0. X is equal to 0, and that probability is 0.5 to the 0 times e to the negative 0.5 over 0 factorial, giving me e to the negative 0.5. Because 0 factorial is 1 and 0.5 to the 0 is also 1. In part B, however, I'm analyzing a different time interval. of 2 seconds. So my probability mass function for the Poisson random variable is going to change because alpha is going to change. Lambda is 2, t is 2, which implies that alpha is equal to 4. So my PMF for this case, the number of arrivals is Poisson for time interval of 2 seconds. So the PMF is going to be alpha to the x times e to the negative alpha or x factorial. X can be 0, 1, 2, and so on. And I'm interested in no more than 2, which means that I'm interested in probability that x is less than or equal to 2. X can be 0, implying 0 arrivals. X can be 1, implying just 1 arrival. Or x can be 2, implying 2 arrivals, but no more. So probability that x is less than or equal to 2 is equal to probability that x is equal to 0 plus probability that x is equal to 1 plus probability that x is equal to 2. I can find these individual terms by plugging in 0, 1, and 2 in the PMF equation. So when I do that, I get 2 to the 0 times e to the negative 2 or 0 factorial plus 2 times e to the negative 2 or 1 factorial plus 4 times. I may have used an incorrect value of alpha. So the correct value of alpha should have been 4. So my apologies here. This should have been 4. So when I use that, I get this should be 4, 2. So now I'll get 4 to the 0 times e to the negative 4 over 0 factorial, 4 to the e to the negative 4 or over 1 factorial plus 4 squared 16 e to the negative 4 over 2. So that should give me 13 e to the negative 4 as the probability that I get no more than 2 packets. Using same principle, please solve part C and turn it as one of your problems for Thursday's class by 10 a.m. In general, whenever you are presented a discrete random variable problem, you can always use this flowchart as a guide as to what to perform, or if you can use any named distribution or named discrete random variable. For example, if a problem is presented to you, ask yourself, hey, does my experiment have Bernoulli trial? If yes, then how many Bernoulli trials are there? If there's just one Bernoulli trial, I'm going to use a Bernoulli RV. If you have multiple Bernoulli trials, ask yourself, are they same? If they are not same, if those Bernoulli trials are not same, then that would mean that you will have to derive your PMF carefully for your problem. This rarely happens. Usually Bernoulli trials are the same in most of the engineering situations involving discrete random variables. If yes, then ask yourself, are you performing fixed number of trials? If you are performing fixed number of trials and you're interested in variable number of successes, then you got to use the PMF of a binomial random variable. If not, then ask yourself, are you performing variable number of trials and you are looking at fixed successes? If yes, then look into how many successes that you are interested in. If you're interested in just one success, use a geometric random variables PMF. If you're interested in n successes, look into Pascal's PMF. If none of these holds true, ask yourself, hey, am I performing one experiment with multiple outcomes? If the answer is yes, then ask yourself, are they equally likely? If the answer is yes, then you're going to use a uniform or random variable. If no, then ask yourself, am I counting the number of arrivals over a time period for a fixed rate? If the answer is yes, use Poisson random variable, otherwise derive your PMF carefully. Most of the problems out there, most of the engineering problems out there, we are lucky with the fact that they can be described using one of these named distributions for which we have nice probability mass functions which we can directly use and perform plugging and chugging of values to calculate probabilities. But there may be cases where you may have to explicitly derive the PMF carefully. In such a case, my recommendation is to use tree diagrams to carefully derive probability mass functions of such problems. We are going to look into such problems in our Thursday's class. Until then, please enjoy my videos. Take care.